Yeah, thank you very much, Simone. And thanks to the organizers for inviting me and giving me the opportunity to speak. And I'd like to give a survey on index theory, on Lorentzian manifolds, and I added for Dirac operators in the title to indicate that I'm not talking about the Fredholm theory that has been successfully used by Andras and his collaborators, mostly for second-order equations, but here I'm really talking about Dirac operators. So the outline of the talk is as follows. After a brief introduction, I will discuss the index theorem in some detail. So we will discuss the boundary conditions that we will impose for how to get Fredholmness. We will see how Feynman propagators enter into the game and how the index can be computed. Then I will sketch an application to quantum field theory. This has been announced by Michal already, and so I have to talk about it. And then in the end, depending on how much time there's left, I will discuss a few extensions and generalizations. All right, so when you look at closed manifolds and you have a differential operator acting on sections of some vector bundle, then it turns out that first order operator, that this operator is Fredholm between the natural Sobolev spaces, let's say from H1 to L2, if and only if this operator is elliptic. And in this case, we have a way to compute the index given by the famous Atiyah-Singer index theorem. And since Fredholmness is equivalent to ellipticity in this case, there is no Lorentzian analog because in the Lorentzian signature, Dirac operators are not elliptic, they are hyperbolic. And so that was pretty much how what I thought about Fredholm theory for Dirac operators in Lorentzian geometry, namely it doesn't exist. However, it turns out that the situation is different if we allow boundary. And so if you have a compact manifold with boundary, then you need to impose boundary conditions. Sometimes you can work with classical local boundary conditions in the sense of Lobatinsky-Shapiro, but often they don't exist, and then you have to take certain non-local boundary conditions, which I'm going to describe. And this has been worked out by Atiyah-Patodi-Singer. And these boundary conditions are named after these three gentlemen. And it turns out that in this case, there is a Lorentzian analog. And that's what I'm going to describe. All right. Now, so the setup is the following. So we have an even dimensional oriented, time-oriented Lorentzian manifold. It's compact with boundary. So you can imagine it like this. It's topologically of the form some closed manifold times a compact interval. So the boundary consists of two components, which I denote by sigma minus and sigma plus. Let's say sigma minus lies in the past of sigma plus. So these boundary components are space-like smooth hypersurfaces, in fact, Cauchy hypersurfaces. And there is a simplifying assumption that I want to make, which is not strictly necessary, namely that the metric is of product form near the boundary. So this is indicated by these light blue regions. So near the boundary, the manifold is metrically a cylinder over the boundary. And then we are given vector bundles, which split into two subbundles. And we have a Dirac-type operator acting on the sections of these two on this bundle. And with respect to the splitting, the operator is odd, so it interchanges the two subbundles. And that's then a hyperbolic operator if the signature is Lorentzian. Dirac-type means that if you square the operator, then you get a wave operator of second order with scalar symbol. Or equivalently, the principal symbol of the operator satisfies the Clifford relations. All right, so that's a Dirac-type operator. Now, on the boundary, you have some induced operators, and maybe I show this also. So along the boundary, this Dirac operator is of the form time derivative, which goes inwards, and some operator which differentiates only tangentially to the boundary. So this way you get an induced, and it's of this product form, since we assumed product structure here. So we get an induced operator on the boundary, A plus and A minus on the two boundary parts. And this is now an elliptic operator. So good, nice elliptic theory for closed manifolds applies to them. However, we are not assuming that these induced operators on the boundary are self-adjoint. In fact, in many cases, we don't even have a metric with respect, a definite metric with respect to which the Dirac operator or these boundary operators are even symmetric. So it's elliptic, but not necessarily the self-adjoint, and that's something we'll have to deal with. Okay, so that's the setup. And now one thing we need to describe are the Atiyah-Patodi-Singer boundary conditions. In the self-adjoint case, if the boundary operator is self-adjoint, you may know how to do it, what that means. You take positive eigenvalues, negative eigenvalues, and you project onto the space spanned by eigenspaces to negative eigenvalues, and you ask your section to lie in this one along the boundary. This does no longer work if the boundary operator on the manifold on the boundary, if the operator induced on the boundary is not self-adjoint, because then the spectrum is no longer real. So we have an elliptic operator on a closed manifold, A plus or A minus, and sigma plus or sigma minus. The spectrum is still discrete. It's an elliptic operator on a closed manifold, but it's no longer real, and it may also have non-trivial Jordan blocks. So we will have to deal with this. Nevertheless, we can write down certain projectors, which will then define somehow what positive and negative eigenvalues should be. First of all, you can define the projector on the generalized kernel. So this is a space on which the operator is nilpotent, and this is by the usual formula. So you take a path encircling the eigenvalue 0 in the complex plane, not encircling any other eigenvalues, and then you take this contour integral and define P0, and that's the projection onto the generalized kernel of the operator A. Now, if we square the operator at this projection, then we get an invertible second-order elliptic operator on our manifold sigma, on the closed manifold sigma, sigma plus or sigma minus, and this is now has then a scalar principal symbol in positive reals, and so by Seeley's work we can define the complex powers of these operators. So these are defined. And then this allows us to write down projectors. So for P plus should be, or P greater should be thought of as the projection onto the sum of eigenspaces to positive eigenvalues. So that's what it's in the self-adjoint case. You write down this formula. Similarly, negative eigenvalues, non-negative eigenvalues, and non-positive eigenvalues. So these are the generalizations that we are going to use. And Atiyah-Patodi-Singer boundary conditions are now defined as a section on your Lorentzian manifold satisfies the conditions if, when restricted to the boundary components, then along sigma minus, the non-negative eigenvalue contributions vanish, and on the other part, the negative ones vanish. The fact that you have two different signs here is related to the fact that Atiyah-Patodi-Singer boundary conditions are always to be taken with respect to the outward normal, but the DT thing is inward pointing on one sigma and outward pointing on the other sigma. So that's why you have these different signs for the two components. All right, so now we know what Atiyah-Patodi-Singer boundary conditions are. Now the first step for an index theorem is that it's the Fredholm property itself. And the claim is that if we look at the Dirac operator on our Lorentzian manifold and impose Atiyah-Patodi-Singer boundary conditions, then this gives us a Fredholm operator. I can do this in smooth sections. I can also use certain finite energy sections. So there are various function spaces which I can use. So for simplicity, let's restrict to the smooth case. And yeah, how is this proof? Why is this true? And here's the sketch of the proof. So one thing that you know is that the Cauchy problem for these kind of Dirac operators is well posed. So if you're given some section along sigma minus, then you can extend it uniquely to a section on the global, on the space-time, such that you have these initial values. And then what you can then do is you start with a section along the left boundary component, you solve this equation with these initial conditions, and then you evaluate at the other boundary component. So this gives us this wave evolution operator, telling us how the wave function evolves over space-time when we start at sigma minus and end up at sigma plus. That's a unitary operator if the Dirac operator is self-adjoint, but it's an isomorphism in any case. Now, we split these L2 spaces, both of them, with respect to these Atiyah-Patodi-Singer boundary conditions, so with respect to these projectors that we have on both these spaces. So we have the range of non-negative eigenvalues and negative eigenvalues. We split this space into these two subspaces, and then this operator can be written as a 2x2 matrix. And then it turns out that these off-diagonal terms that we have here are actually Fourier integral operators of negative order. So a priori, they are of 0 order, but you can do a symbol calculation, and it turns out that the symbol is 0. So it's actually a Fourier integral operator of negative order. And then by the mapping properties of Fourier integral operators, you conclude that as a map on L2, these two off-diagonal terms are actually compact operators. So modulo compact operators, U is actually a block diagonal matrix. And since U itself is invertible, these two blocks then also have to be invertible. So modulo compact operators, U11 and U22 are invertible, and this precisely means that they are Fredholm. So we have these two operators are Fredholm. And once you have that, it's easy to retranslate this into a property of the Dirac operator itself, and to conclude from that the Dirac operator itself is Fredholm. And in fact, the index of the Dirac operator under APS conditions coincides with the index of U22 and with negative index of U11. All right, so that's the reason why this operator is actually Fredholm. And now the question is, what's the index? Can we compute the index similar to the Riemannian case, where you have this very nice formula by Atiyah-Patodi and Singer? And it will turn out that we can. Okay, so let's compute the index. This will then require some preparation, and this is where Feynman propagators enter and play an essential role. If you know index theory in the Riemannian situation, the Riemannian case, then the most popular approach to compute the index is to look at the heat equation and to look at a certain short-time asymptotics of the heat equation and take the coefficients in this heat equation and compute the index from that. This certainly does not work here because it's also completely unphysical. So instead of the heat equation, we use the wave equation itself that we already have on our Lorentzian manifolds and look at certain asymptotic properties of Feynman propagators. All right, so let me be more specifically. So remember, the Feynman propagator is a fundamental solution with a certain condition on its wavefront set. And unlike the advanced and the retarded fundamental solution, Feynman propagators are not unique. They always exist for this kind of wave operator, so we will use it for Dirac squared, but they are not unique. And this non-uniqueness will actually be essential for non-triviality of the index, as we will see. All right, but anyway, so suppose we are given a Feynman propagator of the square of the Dirac operator, then we can, and we give ourselves a certain differentiability degree n, then we can split it, consider it as a bi-distribution on M, and we can split it into a local singular part and into a regular part. The regular part near the diagonal, the regular part is of differentiability Cn, so we can make this as differentiable as we want. And the local part can be described explicitly, the singularity structure. And it's given by such a sum. And these terms that appear here, so these are endomorphism valued smooth sections on the neighborhood of the diagonal, the so-called Hadamard coefficients. So they are smooth. They are recursively determined by certain transport equations. So you can recursively compute them, one after the other, at least in principle. And a very interesting fact is that they are actually the same formal expression as the heat coefficients in the Riemannian situation, of the coefficients of the operator and the metric and the curvature of the manifold. So you have some algebraic, so they can be expressed algebraically in terms of derivatives of the metric curvature and so forth and the coefficients of the operator, and these algebraic expressions are the same as the ones for the heat equation in the Riemannian setting. That's quite surprising at first because they are very different equations. Even the orders are different, at least in time. But the reason for that is that the transport equations, as it turns out, are the same. So that's why this gives us the same formal expressions. All right, so that's something one can in principle compute and encodes some information about the geometry of the manifold. And these other terms that appear here, they are scalar valued, but they are singular. So this is what describes the singularity of this local part. And it's also explicitly given. And in odd dimensions, these are basically powers of the geodesic distance of the 2 points. And in even dimensions, there are also logarithmic terms appearing. And this kind of expansion has been discussed in the physics literature for a long time in various setups, etc. And so that's what we need. And we will actually use this decomposition for n equals 2 moment. So this is how what we will need to know about Feynman propagators. All right, now let's define a Dirac current which directly will relate to the index. Namely, so remember we have the splitting of the Dirac operator as a 2x2 matrix in the off-diagonal terms, mapping left-handed spinors to right-handed spinors and conversely. So let's look at these two parts separately. So dr composed with dl then is a wave operator acting on sections of the bundle SR. And similarly, we can do it in the other order. Then we have a wave operator on the other sub-bundle. And we pick some Feynman propagator for this one, and we pick a Feynman propagator for that one. Then we can apply the previous proposition to it, and we have these Hadamard coefficients of these two Feynman propagators, which are denoted by VRK and VLK. So VRK are the Hadamard coefficients of GR, and similarly for GL. Okay, good. Now, here's the Dirac current. So let's say we take the left-handed Feynman propagator, take its regular part for n equals 2, so that's a C2 function near the diagonal. We differentiate in one component, so we still have something which is C1 here, and then we compose with Clifford multiplication by a vector, so which makes the whole expression linear in the tangent vector x. Evaluate this on the diagonal, and this way this defines us a one form on our manifold. It's of regularity C1. It's of regularity C1 because here we have taken something which is C2. So that's our definition of a Dirac current. And why is this interesting? Well, here's the proposition. Namely, if you compute the codifferential, and we will see this guy in a moment again, if you compute this differential, the codifferential of that, this gives us a function, and then a local computation shows that this can be expressed in terms of these Hadamard coefficients for both VR and VL. And in fact, there's only one degree occurring here, namely the degree of n on 2. So this is for even dimensions. So that's a quite tedious computation, which took us a long time to actually get. But anyway, so there you can do a local computation to compute this. Okay, so we have the Dirac current defined in this way. Its codifferential looks like this. It's expressed in terms of Hadamard coefficients. Good. Now, if you know the Atiyah-Patodi-Singer index formula for Riemannian manifolds, you know that there's a boundary contribution which is called the eta invariant. The eta invariant is usually defined as saying, well, we take all non-zero eigenvalues of our operator on the boundary, and then we take its modulus, raise it to a power s. This gives us some meromorphic function. We extend it and evaluate at 0, and we do a similar thing here, except that we have to be a bit careful because we don't have, the spectrum is not real. So what we simply do then, we rewrite this classical formula as the difference of the positive and negative spectral projection, take the trace for the operator a squared, take the trace and then raise that to the power s on 2 or minus s on 2. So then again, this defines as a meromorphic function if the real part of s is large enough. So then we have a holomorphic function on this half plane in the complex plane, and one can again show that this extends meromorphic to all of C, and that 0 is not a pole, so we can evaluate at 0. And this evaluation at 0 is then, by definition, the eta invariant of the operator. Good. And in addition, we have the dimension of the generalized kernel of the operator. And then we take this combination of eta invariant and the dimension of the generalized kernel and to call this psi of A. So this is the term that will appear in the index formula. Good. So these are the definitions. And now let's look at a special case. Namely, if the manifold is a product. So it's of the form R cross sigma with product metric, and the operator is also of product form. In this case, there is a preferred Feynman propagator. If you're on a product manifold, you can write down a specific Feynman propagator. So, and if you do if you take the Dirac current for that Feynman propagator, remember the definition of the Dirac current used a Feynman propagator, so we had to choose one. And in the case of a product, there's a preferred Feynman propagator, and we take the Dirac current for that Feynman propagator. And then if you insert the full, let's say the future pointing time-like unit normal into this one form, and you get a function, and you integrate it over any spatial slice, sigma, then it turns out that you get the psi invariant for that operator. And in fact, such a formula under certain additional assumption is even true pointwise. So this is a formula which relates the Dirac current for a specific Feynman propagator to the eta invariant or the psi invariant. All right, now we have all the ingredients to compute the index. So we again, remember, we are in the situation that we have a Lorentzian manifold. It's product near the two boundary components, but these are different, right? And so on this product form, we have a preferred Feynman propagator. And here we have another preferred Feynman propagator, and they are in general not the same. So I can take this Feynman propagator and extend it by solving a Cauchy problem over all of M, and similarly for the preferred Feynman propagator coming from sigma plus. And then we have two different Feynman propagators on our spacetime. One induced by sigma minus and the other one induced by sigma plus. And then we have two associated Dirac currents for that. So let's look at the difference of these two Dirac currents and define this as the relative Dirac current. And then this codifferential is certainly 0 because we have computed the codifferential of these things, and it was expressed in terms on Hadamard coefficients, which do not depend on the choice of Feynman propagator. Only the regular part of the Feynman propagator depends on its choice, whereas the local singular part is always the same for all Feynman propagators. So then we have that this is actually a co-closed one form, and this allows us now to compute the index. Namely, after a little computation, you can check that, working with certain projectors, you can check that the index of our Dirac operator under APS conditions is the same as the integral over some manifold, over some Cauchy surface of the relative Dirac current applied to this unit future normal field. And we can take any sigma because of this property here. So it doesn't, by the divergence theorem, it doesn't really matter which Cauchy hypersurface we are using for this computation. And so let's make a choice. Let's say we pick sigma plus for our sigma. So we want to compute this, this integral. No longer working. So we want to compute this integral by choosing sigma to be sigma plus. And J is the difference of J sigma plus and J sigma minus, so let's write that down. And then we see this first term, that is nice, that fits. Here we have the sigma plus current integrated over sigma plus, and by the previous proposition we know that we get the psi invariant for that. But the second term doesn't quite fit because we integrate over sigma plus, but we have the current for sigma minus, so this doesn't match. So the first one gives us exactly this by the previous proposition. The second one needs to be corrected. So we want to turn this into an integral over sigma minus, and to do that, I use the divergence theorem. So I get the integral over sigma minus and the correction term by Gauss's divergence theorem involving the codifferential of this Dirac current. Now we have everything we want. Namely, this is now again good because this gives us the psi invariant of A minus, and this one gives us this integral of Hadamard coefficients. In that way, we found our index theorem. So the index can be computed by a boundary contribution involving the psi invariant, the spectral thing, and an inner integral involving these Hadamard coefficients. If you now look at the special case of twisted spinorial Dirac operators, so you have a spinorial Dirac operator, you twist it with a Hermitian vector bundle, then this part here can be identified by the usual formula for the Riemannian case, where you take the A hat class of the Levi-Civita connection. So this involves the curvature of the spacetime, and this is the twisting bundle, the Chern character of the twisting bundle, if you have one. And the reason why we get that is, remember I told you that these Hadamard coefficients are the same expressions in terms of curvatures and coefficients of operators as in the Riemannian case for the heat equation. And for the heat equation, we know what we get. By Getzler's rescaling trick, we know that we get this expression. So we can conclude this without any computation, actually. So that's for the special case of twisted spinorial Dirac operators. But this formula, as it stands here, is true for any Dirac-type operators, this form. Okay, so that's the index formula. And I told you in the beginning that we can actually drop this assumption of having product structures near the boundary. And if you drop that, you get an additional boundary contribution coming from the so you take this integrand that you have in the interior here, and you can get a so-called transgression form for that, and you have to integrate this over the boundary. So you have an additional boundary contribution in this case. This part is 0 if you have product structure, but it's not 0 in general. And this term is more similar to that term because it's a local integral, or integral over something locally computable, while these boundary contributions here are global, they are spectral. Okay. And so that's also exactly the formally the exact same formula as in the Riemannian case, remarkably. Okay, so that's the index theorem. And now I want to sketch an application to quantum field theory. And this concerns the chiral anomaly. So an anomaly is something, of course, for the physicists in the room, anomaly is something that's when some quantity which is preserved in the classical setting all of a sudden is no longer preserved after quantization. And in this case, it's the chirality of our particles. And so in the framework of algebraic quantum field theory and curved spacetime, you can make this mathematically rigorous, what I'm saying here. So you have a right-handed charge, which you can write down, and you have a left-handed charge, and the difference of the two are the relative chiral charge, so some would be the relative total charge. And these things can be defined. I don't have time to go through this. But anyway, so we have these quantities, and in a way, it's not surprising that we have a physical interpretation for the index of the Atiyah-Patodi-Singer index theorem, because what do APS boundary conditions mean? You have this splitting into positive and negative eigenspaces or eigenmodes, and you put one of them equal to 0. And in physics, this corresponds to particles and antiparticles, this splitting. And so in some way, you may think of this as particles turning into antiparticles. So the net amount is measured by the index. And this can be, okay, thank you. Thanks. This way, it's not surprising that we can get some relation to this chiral anomaly. In fact, for the Riemannian situation, I don't know of any physical interpretation of the APS boundary conditions. But in the Lorentzian case, it seems quite natural. And so we can define these quantities, well defined in the framework of algebraic quantum field theory on curved spacetimes. And then it turns out that these relative charges are directly related to the index of the Dirac operator with APS boundary conditions. And so then we can write down, we can insert our index formula for this index, and we get a geometric formula for the relative chiral charge that way. And remarkably, this formula had been used already in the 1970s by physicists to compute the chiral anomaly, even though the index theorem was not available, of course, at the time, but they just applied the Riemannian index formula and ignoring the fact that it was completely unclear whether this makes any sense in the Lorentzian setting. They just did it anyway. And so as it turns out, the theorem, that approach was correct because, as it turns out, the index formula is formally the same as in the Riemannian case. And that's why at least some of these computations in the physics literature gave actually, in fact, the correct result. So let me briefly discuss two examples. Namely, one is two-dimensional, 1 + 1 dimensional. So the manifold is just time interval times S1, so that's our space. And we just take the product metric, very simple. We have the spinorial Dirac operator, and the non-triviality comes into play by the twist. So we twist with a connection, which is just given by one function multiplied by d theta. So this corresponds to an electric field without magnetic component, 1 + 1 dimensions. And in that case, the A hat part in the index formula is trivial because this has only contributions in dimensions divisible by 4. So that's two-dimensional. But we have this Chern character term, which turns out to be essentially the curvature of this connection, which you can then compute easily. So then this inner integral in the index formula can be easily computed, and you just get the difference of the A function that enters in this ansatz times L, which is the length of the circle. Okay, so much about the inner part. But then we also have the psi contribution. And here it's interesting that now this depends on the choice of spin structure. Namely, S1 has two spin structures, and the spectrum of the Dirac operator on S1 depends on the choice of spin structure. And so also the eta invariant and the psi invariant depend on the choice of spin structure. And if you compute it using some Riemann-Hurwitz functions, then you get two similar but not quite the same formulas for the index. So that's an example that shows that the index in general will depend on the choice of spin structure of your space-time. Such a thing does not happen in the classical Atiyah-Singer index theorem, where you have closed manifolds, because in that case, you only have this inner integral giving your index, and that's always determined by local quantities, and the spin structure does not enter. But if you have a boundary, then the eta invariant of the boundary enters, and in this way, the choice of spin structure can affect the result. And this is probably the simplest example where this happens. That's a textbook example that you can find in QFT books, actually. And here's another example that was computed in 4 dimensions by Gibbons, but you can do it in any dimension divisible by 4. So you take a sphere, 4k minus 1 dimensional. So that's our space, cross it with a compact time interval. And now your metric is no longer a product metric because we choose a time-dependent metric on the sphere, which has to be chosen properly. And so these are certain Berger metrics, as they're called. So you can write them down explicitly. They are not quite the standard metric on the sphere, but the second simplest metrics that you have on these spheres. And then again, you look at the spinorial Dirac operator, no twist in this case, and then you can compute for suitable choices of t values and this family of operators that your index takes this form. So it's also non-trivial. And for k equals 1, which corresponds to the 4-dimensional case, this has been computed by Gibbons in 1979. Okay, so that's an application to quantum field theory. And now I would like to talk about some generalizations and extensions. And there are various directions in which you can extend this index theorem. Maybe the first question is, what about different boundary conditions? So we have only talked about, so far, we have only talked about very specific boundary conditions, namely the ones given by Atiyah-Patodi and Singer. So what else could you take? And there it's good to first take a somewhat abstract view on the matter. And this can be conveniently formulated in the language of Fredholm pairs. So what's a Fredholm pair? So you have a Hilbert space, you have two closed subspaces, linear subspaces, and then these linear subspaces, or the pair of these subspaces, is called a Fredholm pair if they are almost a direct decomposition of your Hilbert space, in the sense that the intersection may not be 0, but it's finite dimensional, and the sum may not be the whole space, but it's closed and of finite codimension. So similar to a Fredholm operator being one which is invertible up to finite dimensional errors, a Fredholm pair is a decomposition of your Hilbert space as a direct sum up to finite dimensional errors, roughly speaking. Okay, and then the index of this Fredholm pair is defined to be the dimension of the intersection minus the dimension of, or the codimension of the sum. Okay, and here are some elementary properties of Fredholm pairs. The first one is totally trivial, so the order doesn't matter. And the second one is if you pass to orthogonal complements, replace B0 by its orthogonal complement and do the same thing with B1, then you again get a Fredholm pair, and the index is just a negative. Easy to check. And the other one, next one is also not hard to check, but very useful. If you change one of your subspaces in your Fredholm pair and you replace it by something which somehow differs only by some finite dimensional stuff. So let's say we take a bigger space, but the dimension of the quotient is finite. Then replacing B0 by B0 prime gives you again a Fredholm pair. And in the index is corrected by what you expect, namely by this dimension change of this pair. So this way you can modify things by finite dimensional stuff and stay in this class of Fredholm pairs. All right, so that's the general abstract notion. And now here's the observation. Namely, so suppose you have closed subspaces in the L2 spaces of your two boundary components, sigma plus and sigma minus. B plus in sigma plus, L2 of sigma plus, B minus in L2 of sigma minus, closed linear subspaces. And remember, we have this wave evolution operator taking sections from sigma minus to sigma plus by solving the homogeneous Dirac equation. Now the following are equivalent. So these are subspaces of two different Hilbert spaces. But what you can do is you can look at the Hilbert space L2 of sigma minus and use this isomorphism to pull back the subspace of the other one. So you take B plus, pull it back by this map, and then you have two subspaces of L2 sigma minus. And the first condition is that this is a Fredholm pair of index K. You can do the same thing by pushing forward this other thing and work in the Hilbert space, in the other Hilbert space, sigma L2 of sigma plus. And then this is a Fredholm pair of index K. The equivalence of these two is of course obvious because U is an isomorphism, just mapping the subspaces from one space to subspaces in the other space. The interesting thing is the equivalence to the Dirac operator, subject to the boundary conditions that when we restrict to these sigmas, then you land in these subspaces. So these are the boundary conditions, and that this gives you a Fredholm operator of index K. So that's equivalent. So the Fredholm property of your Dirac operator under the boundary conditions, restriction to sigma minus is in some specified space, and the restriction to sigma plus is in some specified space. This is Fredholm of a certain index can be formulated in terms of these Fredholm pairs using the Dirac evolution. Okay, And now these elementary properties of Fredholm pairs allow your first conclusions. Namely, if we start with, so we can replace our spaces by their orthogonal complements. So if we do this for Atiyah-Patodi-Singer boundary conditions, for which we know they are Fredholm, we've just proved it, we can replace them by their orthogonal complements. So instead of positive spectral projector, I replace it by the negative one, and conversely, this we might call anti-APS boundary conditions. And this is then will also give us a Fredholm operator. And the index is just then the negative one of APS. And this is remarkable in the sense that this is completely false in the Riemannian case. If in the Riemannian case, you replace APS conditions by anti-APS conditions, you will not get a Fredholm operator. But in the Lorentzian case, you will, as we see from the simple argument. And you might think of this as follows. In the Lorentzian case, we are looking at wave equations. They can be solved forwards and backwards. That's equivalent. Whereas in the Riemannian case, we are looking at a heat equation, which can be only solved in one direction. So that's really what's behind this difference. Anyway, so here in the Lorentzian case, it doesn't really matter whether we take APS or anti-APS. And the second one is also interesting because we can start to modify our APS conditions by finite dimensional stuff and still get a Fredholm condition. So for example, instead of looking at APS conditions, we could take APS plus some finite sum of eigenspaces. So we could relax or make the condition stricter. We will always get a Fredholm operator, and the index will then be corrected by the dimension of the space we have added or removed. So that's, and then we can start from the geometric index formula for APS and compute the index also for this kind of modified APS boundary conditions. You could also do some crazy stuff like you could say, well, why not take B plus all of L2 and B0, 0? That also gives you a Fredholm pair, obviously. And then you would also say, okay, then you get a Fredholm operator here, but that would mean you impose no condition on one boundary and you equate it to 0 on the other boundary component. And then the fact that this is Fredholm is, of course, a direct consequence of the well-posedness of the Cauchy problem. But that's also included somehow in this picture. Okay. All right, now that's one extension. And in fact, we have then studied this together with Sebastian Hannes, studied this to write down certain explicit boundary conditions which are Fredholm for the Lorentzian Dirac operator. We have also found some which are, so remember, APS is Fredholm in the Lorentzian case, but not in the Riemannian case. We also found other conditions which are Fredholm in the Riemannian case, but not in the Lorentzian case. And in the Riemannian case, one has a complete understanding of when these boundary conditions give you a Fredholm operator. In the Lorentzian case, we are not quite there yet. We have some sufficient criteria for Fredholmness of certain boundary conditions, but we do not have a complete characterization yet. Right, now another extension of our index theorem would involve dropping spatial compactness. Right? So we have assumed that our Cauchy surfaces sigma are compact. If you drop spatial compactness, this is like in the Riemannian case talking about index theory for non-compact manifolds, which in general is of course not possible because these operators for the Dirac operator on Rn is not Fredholm, for instance. But one can maybe make some restrictive assumptions to also work on certain non-compact manifolds. And that's what we want to do here. So we want to keep compactness in the time direction as it is. So we have a finite time range, but we want to drop the spatial compactness. And there are two ways known so far what one can do. And the first one is we drop compactness of sigma, but we restrict our operator as follows. So we look at the spinorial Dirac operator, possibly twisted, and we add to it a potential, psi, zero order potential, the so-called Callias potential. I don't want to go in all the technicalities of the definition of Callias potential. The most important condition that it has to satisfy is a certain growth condition as you move to spatial infinity. So it has to grow at a certain rate. And this is what restores Fredholmness, even though the manifold is non-compact, as it turns out. And so one has to also make the assumption that there's a compact set in your sigma such that outside this compact set, everything is of product structure and independent of T. And then it turns out, and it has been proved by Braverman, that in this setup, for this so-called Callias-type operators, the APS conditions give you a Fredholm operator, and the index formula is the same as we have seen before, except that the Xi invariant, so the individual Xi invariants are no longer defined on our non-compact manifolds, but a relative version of the Xi invariant, which in our case would be just the difference, is still defined. So the individual Xi invariants are no longer defined, but the difference is still defined. And that's then called the relative Xi invariant. You also have to be a bit careful. You have to also think about to what extent these things make sense. Since our manifold is now non-compact, does this integral actually exist? It does exist because these integrands are actually zero outside this compact set K or time interval times K because of this product structure assumption. So in actual fact, even though these manifolds are non-compact, the integrands have compact support, so these things are well defined. So that's due to Braverman. And here's another way to drop spatial compactness. It's very different. And in this case, we look at operators which are not Fredholm actually, in the conventional sense, but we broaden our concept of Fredholmness. And this works as follows. So we have, again, a globally hyperbolic manifold, still temporally compact, but the Cauchy surfaces are no longer compact. Still, the boundary consists of sigma plus and sigma minus. And now we have a group acting on our manifold, probably discontinuously, so that you have a nice quotient, and by isometries. And then, since this acts by diffeomorphism, it has to preserve the boundary. And I want to assume that these two boundary components do not get mixed. So our group, should preserve these boundary components. So in particular, they act on the boundary components. And the assumption is that this action is co-compact in the sense that the quotient is something compact. And we want ourselves to be given a gamma-compatible spin structure so that the Dirac operator will then commute with the action of this group on spinners. Here's an example. You could take as your manifold Rn with the Euclidean metric times time interval, and you take this Minkowski metric here. So it's really a strip in Minkowski space. And your sigmas are just these two time slices, the two boundary hyperplanes bounding your strip. And as your group, you might take the integers acting by translations in spatial directions. So that's the simplest example. And so this way, you can deal with these strips in Minkowski space, even though the Dirac operator is not Fredholm for this in the conventional sense. Now, what is the result then? Well, the result is that the spinorial Dirac operator in that setting with APS boundary conditions or also anti-APS boundary conditions is gamma Fredholm. And what is that supposed to mean? Well, we have this gamma action. The kernel, for example, of the operator is in general infinite dimensional, but there is a gamma action on it. And if you have a Hilbert space with an action of such a group, then you can look at all bounded operators of that Hilbert space commuting with the group action. And that's a von Neumann algebra. And this algebra has a canonical trace. And now you can define dimensions of subspaces by saying, okay, if I have a subspace, I take the orthogonal projection onto that subspace and apply the trace to the projector. Right? So in finite dimensions, if you have a subspace of a vector space, you could characterize the dimension of the subspace by saying, look at the projector onto that subspace and take its trace. This gives you the dimension. And you imitate this using this von Neumann trace of the von Neumann algebra of gamma equivariant bounded operators. And then gamma Fredholmness means that this gamma dimension of the kernel is finite, and similarly for the co-kernel. So that's what it means. And in that sense, it's actually gamma Fredholm. This gamma dimension can actually be any positive real. So it's no longer in general an integer. So a priori, the index could also be an integer, a non-integer. But unfortunately, what we are here missing still is an actual computation of the index. A similar thing in the Riemannian setting is well known. That's Atiyah's L2 index theorem, where you have exactly the same situation. You have a non-compact manifold, you have this gamma action, you have a compact quotient, and then you have also this gamma index. And then Atiyah tells us that the gamma index on the non-compact manifold coincides actually with the conventional index on the compact quotient. That's something which is a priori not clear at all, because if you compute the conventional index of the quotient, this corresponds to periodic functions on the covering. Whereas if you compute this gamma index, you look at L2 functions and look at their gamma dimension. So you look at really very different solutions of the Dirac equation. Nevertheless, Atiyah tells us that in the Riemannian case, they coincide, and I'm very confident that the same thing will be true in the Lorentzian case, but there's no proof yet. So Damaschke has announced results in this direction, but I haven't seen anything yet. All right, so these are very different approaches to dropping spatial compactness, and let me conclude by mentioning how one might drop temporal compactness. So in this case, we keep the Cauchy surface compact, but we now have non-compact time. So a manifold is R cross sigma with a metric of this form. That's the general form a globally hyperbolic metric can take. It's spin and even dimensional. And we assume that the metric is asymptotically static as we go to plus and minus time infinity. So this function in front of the metric should converge to a smooth function on sigma, positive smooth function, as t goes to plus and minus infinity. And similarly, these metrics should converge, and they should do so with a certain prescribed decay. And then we look at the spinorial Dirac operator, and then it turns out that then again, we get a Fredholm operator on suitably weighted function spaces. And the index of this Dirac operator with APS boundary conditions is again of the same form as we have seen earlier, except here, this contribution of the transgression form is now at times plus and minus infinity. So you have to first compactify your time in a suitable way and then write down. Then you can write down this one, transgression contribution. And that's due to Michal and Shen from last year. And with this, I would like to conclude and thank you for your attention.